Heyo, what's crack-a-lackin'? It's your boy. So today we'll go over equilibrium, like from A to Z, so topic 7 and 17. And these are just the notes I guess my teacher uses, but I thought it would be good if I just went over this and explained it in a bit more detail, just so I know what to hit when I'm talking about this stuff. I'm going to start off with chemical equilibrium. What that is essentially a reaction where the rates of forward and backwards reaction are the same. That doesn't necessarily mean that the concentration of, for example, HI is equal to the concentrations of this and this. That's not what it means at all. It just means that the time or the rate at which this changes to this is equal to the rate at which this changes to this. In other words, the concentration of HI and the concentrations of H2 and I2 stay the same. They don't necessarily have to be equal, but they just stay the same. This is an example of an equilibrium, a common equilibrium actually. And these are just graphs which explain two situations which are happening here. So let's break this down. In the beginning of the reaction, it says that HI begins at 0 concentration. So we start with no HI. However, at time equals 0, we start with loads of product, H2 and I2. The reaction shows that as time goes on, H2 and I2 decrease as more HI is being made from those products. Eventually, however, the concentrations of HI plateau. It stays the same, while the concentration of H2 and I2 also plateau. This indicates equilibrium because one of the criteria we said defines equilibrium is the fact that the concentrations don't change. The point where the concentrations don't change also indicates a point where the rates of forward and backwards reactions are the same. Now, a similar graph is used here to explain a little bit of a different situation. We start off with 0 H2 and I2, and we start off with all HI, but as HI, our reactants decompose to form H2I2, right, as H2I2 increases because HI is decomposing into this, eventually we'll reach a plateau where the concentration doesn't change. This, again, indicates equilibrium, but there's a subtle difference here. Here, H2I2 really doesn't change too much. It increases instead of decreases, which means that equilibrium is being approached as H2I2 increases. So we're approaching it in this direction, right? Because in this direction, HI decreases while H2I2, these two increase in concentration. The opposite can be said for this graph right here, because equilibrium is being approached as H2 and I2 increase and as HI decreases. So in effect, we're approaching equilibrium this way. Yeah. Graphs aren't too important to know, but if anything, I hope that broke it down a bit. This just states exactly what not what I said, but it's good to know. If there are more products than reactants, the products are favored. If there's more reactants than products, the reactants are favored. This outlines the fact that in equilibrium, the concentrations aren't the same, but the concentrations must be constant. Here are a couple of characteristics. They're dynamic, so the reaction is still going. It just seems like it's stopped or that it's constant because the rate of forward and backwards reaction are occurring equally, are at the same rate. It must be in a closed system. The reactant and product concentrations remain the same. No changes in macroscopic properties, which means because the concentrations don't change, the chemical composition of the reaction mixture also doesn't change. So there's no change in the macroscopic properties. And it can be reached from either direction. Again, as we indicated that in this graph right here, equilibrium was being reached in this direction, and in this graph it was being reached in this direction. The equilibrium law essentially gives us a way we can describe the relative concentrations of products and reactants. In its most basic form, Kc is just the concentration of products over the concentration of reactants, which in effect, according to this, is just C D over A B. Notice that the stoichiometric coefficients are also included in this equation. With respect to the equilibrium constant Kc, the stoichiometric coefficients need to be the powers of each constituent concentration. So then this becomes C, D, A, B. These are the letters I'm getting these coefficients from. Again, Kc, as it says here, let me highlight that. Kc is a measure to the extent which a reaction occurs. It varies with temperature and only with temperature. So if a question asks you what effect does pressure have on the Kc, nothing. The only time your Kc can vary is if you change the temperature. So keep that in mind. Let's do some examples. Kc here is equal to our products over reactants raised to their stoichiometric coefficients. Now, the first thing you want to see if the equation here is balanced, and it is, so you don't need to worry. This is PCl3, Cl2 over PCl5. Simple enough. Let's do the same for this one. Kc here is equal to NO4, H2O, 6, NH3, 4, O2, 5. On the side, I just have these slides just to make sure I'm saying the right stuff, because I just want to make sure my answers here are correct. Again, it's good practice just to make sure the equations are balanced, because sometimes they don't do that. So it says here, 1 liter of the equilibrium mixture from sample A was found to contain 0.172 mole PCl3, 0.086 mole Cl2, and 0.028 PCl5. So in this equation, or in this question, we have to do two things. You have to first find out what the equilibrium constant is, and then we have to plug in the concentrations. So let's do that. We know that from the above, Kc is just this. So Kc is then equal to the concentration of PCl3, which is 0.172 mole in a 1 liter container. So our concentration is just all this divided by 1, which in fact doesn't change anything. Another thing to note is that when we're using concentration and it gives us mole, we need to find moles per liter, or moles per decimeter cubed. And to do that, we need to see what the volume of our reaction chamber or space is, and we divide all our mole values by the volume. Sometimes IB will give you a container which isn't 1 liter, and unfortunately, if you don't, do the whole molar shebang, the whatever, you won't get the Kc right. So you're gonna want to do 0.172, and the concentration of Cl2, which is 0.086, over 0.028. And if you plug this in, as they did here, you'd get 0.53. Another thing to note, it's quite important, actually. Let's get the red, because it's important. When Kc is greater than 1, there are more products than reactants, and when Kc is less than 1, there's more reactants than products. And this makes sense, because if we go back here, if products is greater than reactants, then this fraction must be greater than 1. If reactants is greater than products, then our fraction must be less than 1. Okay, reaction quotients. This is cool because reaction quotient is essentially the same formula as Kc, but you're using non-equilibrium concentrations. Note, for example, in this question, it gave us strictly equilibrium concentrations, as it indicates here. But you can still use the equation without having equilibrium concentrations, and we'll talk about those implications later and why that's important. But when we're comparing Q and K, and Q is less than K, then the implication is that in order to approach K, you're going to need more products, right? Because if Q is less than K, our fraction is less than K, which in effect means we need more products to get to K. Another way you can envision this, if this K is right here and Q is less than it on a number line, then you have to go this way towards the product side. The products right here to get to K. If Q equals K, then we're already at equilibrium. There's no problem. And if Q is greater than K, again on our number line, K is right here and Q is right here, we'd have to go this way, which approaches the reactant side. So we need to approach the reactant side to get to K. Let's see what this slide here says. Yep. So you can say it proceeds to the right, or you can say it proceeds to the product side. Either or works. So let's put that down. Cool. Let's do this question. Kc for this reaction at 450 degrees C is 49. So it gives us the Kc. Now it gives us the moles, and it gives us the liters. So automatically we know that because it's just 1 liter, all our molar quantities, our mole per decimeter, is just our mole quantities here because we're just dividing by 1. So it gives us the concentration, but not at equilibrium. So because we're not at equilibrium, we're going to have to say Q instead of Kc. First, we need to find what this reaction quotient is. And this is just the same thing as the equilibrium quotients, or the equilibrium constants, sorry. You plug this in. Now, what does it tell us about HI? It says 0.66. However, because the stoichiometric coefficient is 2, we must raise it to the second power. H2 is 0.22. I2 is also 0.22. And I don't want to do the math, so I'm going to scroll down here, and we get 9.0. Now, here's the comparison to make. Is Q greater than or is Q less than Kc? Well, we got 9.0. 9.0 is less than 49. So Q is less than Kc. What does this imply? Well, this implies if we look up here, this implies that we must proceed to the right in order to reach Kc. Is that what this says here? So the forward reaction predominates. That's the same as going to the right. Again, there's many different ways to say it. I just like saying that. So in a system at equilibrium in a 1 liter container, we find 0.25 mole PCl. Again, this is 1 liter, so you don't have to worry about converting to molar because you're just dividing by 1. 0.25 mole PCl, 0.16 mole PCl3. What equilibrium concentration of Cl2 must be present? So this one's a bit cool because it gives us the Kc. So let's first evaluate what this is. It's just going to be PCl5 over Cl2, PCl3. Again, because that's what we get from this reaction. And that is equal to 1.9. Now, what do we know? We know for sure that PCl5 is 0.25. Cl2 is... we don't know, so we're going to just leave that Cl2. And then PCl3 is 0.16. And that should equal 1.9. So by a little bit of algebra, which I'm not going to do because that's tedious, and with a little bit of calculator work, which I'm also not going to do because the answer is right here, is you get 0.82 mole per liter. Remember your units. When equilibrium is disrupted, so are we going to, we're going to talk about something called Le Chatelier's principle. What is that? Le Chatelier's principle essentially states, it's a rule that states that when you add a stress to a solution at equilibrium, then that equilibrium is going to respond in a way to reduce that stress. IB likes to ask, from what I've seen at least, and the questions I've come into or run into on past exam papers, is they're typically the three they talk about. There are other ones involving acids, bases, acids and bases, but that's something you'll learn more about when you learn about acids and bases and conjugate acids and bases and stuff like that. But for right now, we're going to focus on these three. So the three factors are concentration, temperature, and pressure. Let's talk about concentration. Concentration. Consider this reaction at equilibrium. H2 plus I2 equals 2HI, or at equilibrium with 2HI. So what would happen if we added some H2? Let's think about this. So we have, whoa, look at all this H2 we now have because we add it. What will the equilibrium want to do? Well, it will want to use up this excess H2, so it doesn't have as much of it. Remember, we want to reduce the stress. So how do we do that? Well, we create more product. What does this mean? The equilibrium shifts more to the right. So what will happen to equilibrium? It shifts to the right. What happens if we remove the H2? So if we remove H2, oh no, we have less H2 now. What will the equilibrium want to do? It will want to reverse this. So it will decompose some of its product to replenish the lost H2. What does this mean? The equilibrium shifts to the left. So it shifts left. And let's see if this is in agreement with me. Now, I honestly couldn't tell you anymore. Oh, well, here it is, actually. Yeah. So we're in agreement with the slides. Changes in temperature. So consider this reaction at equilibrium. 2SO2 plus O2 is in equilibrium with 2SO3. And recall, this doesn't have it. The delta H, or change in enthalpy, is positive, which indicates an endothermic reaction. What I like to do to kind of make this a bit more implied for me is creating heat as a product, as a reactant. Because in an endothermic reaction, we're consuming heat to produce the reaction. So let's see what this says here. What will happen to equilibrium if we increase the temperature? Well, kind of like the products, if we have lots of heat, the equilibrium will want to get rid of as much heat as possible. So what it does is it tends towards the product where it consumes it in the endothermic reaction. We're favoring the endothermic reaction because it helps us consume the heat that we don't want. So we say that the equilibrium shifts right. What happened if we decrease the pressure? I meant right here. Equilibrium shifts right. What happens if we decrease the temperature? Now our reaction mixture is really cold and we want some more heat. We want to reverse the effect of cooling it down. We're going to want to tend this way so that our heat, we create some more. So then we say that it shifts left. You can also say that the reverse reaction is exothermic. Therefore, we want to favor the exothermic reverse the reaction. Shifts left. Oh, I meant to say left. That's what I meant to say. So yeah, that's change in temperature. Let's do change in pressure. Consider this reaction at equilibrium. 2NO2 at equilibrium with N2O. What will happen to the equilibrium if we A, increase the pressure? Well, let's think about this. If we increase the pressure, we decrease the volume. So say we go, this is our reaction chamber. If we increase the pressure, it suddenly becomes something like this. Now, to reverse the pressure, we're going to want to tend to the side of equilibrium. Oops, where did that go? We want to tend to the side that has less moles of gas, so we occupy less volume for the volume we've now decreased in our reaction chamber. So we're going to want to tend to the right. shift right. Because recall, or notice, well, what do you mean recall? Notice this is 1 mole of N2O. This is 2 mole of NO2. So we'd be occupying less space if we tended towards N2O4. If we decrease the pressure, we create larger space, so equilibrium will shift to the side that occupies more space, which in this case is 2NO2. So it shifts left. How will an increase in pressure affect equilibrium? So if we increase pressure, we decrease volume, so we tend to the side with less moles of gas. So this is just 9 moles of gas, this is 10 moles of gas, so we shift left. This is 3 moles of gas, this is 2 moles of gas, so we shift to the right. Shift right. How will an increase in temperature affect the equilibrium? So, if we have heat as a product, increasing temperature, we'll want to get rid of that heat. So we'll go this way. That way, we shift left. Now this is endo. So if we increase the temperature, we go opposite the heat. We want to get rid of it. So we shift right. This is endo, so heat is a product. We'll shift opposite to the heat, so we shift right again. Okay, so the Haber process, essentially it's an equilibrium between, let me write it out, H2 plus N2 to produce something called ammonia. And ammonia is important because fertilizers need ammonia to nourish plants. These plants then a process known as nitrification convert ammonia to other nitrogenous compounds that they can use to assimilate nutrients and grow and recycle back into the environment. All this important stuff to grow plants. And of course, you want to make sure you have your states. So these are all in the gaseous phase. And you also want to make sure you balance. So then that would be 3, and that would be 2. So, some notes here. Just really know it's important. You don't need to know these stats. These are great. Now the forward reaction is, correct me if I'm wrong, let me check here, I don't quite remember. You don't need to know this. The question will usually give you the balanced equation. But so it's an exothermic process, because delta H is negative. So that's what it is. How would the equilibrium be influenced by increasing the temp? Well, it's an endothermic reaction, which means heat is a product, which means we want to get away from the heat, we want to use up the heat, so we tend to the left. Shift left. Decreasing temp, we want to increase the temperature, so we want to go right. Because if we make it colder, we want to make it hotter, kind of thing. We want to reverse the effect. Increasing the pressure by decreasing the volume. This is a bit redundant. You should just say increasing the pressure. If we increase the pressure, we tend to the side with less moles of gas, so we shift right. Decreasing the pressure. If we decrease the pressure, we increase the volume, so we tend to the side that would occupy more volume, so the side with more moles of gas, so we shift left. Increasing pressure by adding an inert gas. This one is a bit controversial in our class. Inert gases apparently don't react with anything, so in effect, it doesn't really shift the equilibrium, but it does say increase pressure, so you might say, well, if we increase the pressure, we should shift right. I'll leave that open to you to interpret. We'll see what the side here actually says. Yeah, that's weird. Well, we're going to stick with the no change. for now, even though I don't really agree. Adding more H2, well, if we add more H2, we'll go to the opposite side to use it up, so we shift rights. If we remove some NH3, we'd want to replenish more NH3, so we shift to rights. Shift rights. If we add a catalyst, we're increasing the rate of forward and reverse reactions to the same degree, so there's no net change in rate and there's no net change in concentration, so equilibrium wouldn't be shifted. It wouldn't be affected, so no effect. No effect. Optimum conditions for Haber process. Concentration. Well, let's see. Well, we'd want to keep the concentrations of the reactants high. Why? So it tends more towards the right, and our yield of NH3 increases. Pressure, we want to keep the pressure relatively high, so we tend to the right where there's less moles of gas, or in other words, less moles of NH3. Temperature, now this is a bit finicky because we want the temperature to be low to favor the product side, but if it's too low, then we also inhibit the movement of colliding particles, which in turn inhibits the rate of reaction. So we want to strike a relatively good medium. So let's say medium. And catalyst, the catalyst doesn't shift the equilibrium, but it makes sure that we reach it faster. So catalyst, typically we use an iron 3 catalysts. The contact process. Do I want to go over this? So I don't think we need to know this, so I'm not going to go over it. But for the sake of whatever, I'm going to still do it. Pressure, if we look at this balanced equation, if you notice, if we increase the pressure, we tend towards this side because there's less moles of gas, so we want high pressure. Now, it's an exothermic reaction. So if we increase temperature, we favor this side. So in effect, we want to decrease temperature. But remember, if we decrease it too much, we inhibit the reaction or its rate. So we'll say medium. Again, medium is a bit of a vague term, but that's kind of that. And catalyst, we use a vanadium oxide catalyst. Okay, homogeneous equilibria calculations. Here we're using something called the icebox method to determine equilibrium concentrations, which in effect help us determine Kc at a given temperature and with a given set of starting concentrations. So this is going to taper in to the HL part. So if you're SL, you don't have to look at this part, but if you're interested, you can. I'm just going to grab my syllabus real quick so I know what to talk about. So if you don't mind, I'm just going to go fetch that real quick. Okay, so from what I'm seeing here, can't really find it. Okay, yeah, got it. Just a bit messy here. Okay. Here it is. I'm just looking if you need to know anything outside of this that haven't covered. No, okay. So, homogeneous equilibria calculations. This is what we use called an icebox. So let's do that. We're gonna have I for initial, C for for change in concentration, E for equilibrium concentration. Now you always want to start with a balanced equation. So right here we have H2 and Cl2, and we know that will go on to create HCl. So that is H2 plus, remember your phases too, H2 plus Cl2 yields HClG, and we're going to put a 2 there, just keep it balanced. Okay, so with this one, it gives us moles and it gives us volume, but the volume is 2 liters. So what do? We know that concentration is mole over volume, so we divide all these by 2. So this becomes 2, this becomes 3. And this 2 moles HCl becomes 1. We also need to put our reactants down. So we have H2, we have Cl2, and then we have 2HCl. So initially, we have H2 is equal to 2, right? Because that's the molar concentration that we calculated. 3, and the question doesn't specify how much HCl there is, so there's 0. We also know that at equilibrium, there is 1 mole per decimeter of HCl. So this gives us more than enough information to solve this. And you might be like, well, how? Well, I'll show you. To get from 0 to 1, that's just adding 1, right? The change in concentration is 1 mole per liter. Now, what's the change? If this is adding 1, we know that to get products, we need to remove reactants. But how much do we remove? What's the change? Well, if the stoichiometric coefficient is 2 here and it's 1 here, then this must be 0.5 here and 0.5 here, because it's a 1 to 2 ratio. So you only take half. So you have negative, negative, and then positive 1. Which in effect means this is 1.5, and this is 1.5. So you can very easily calculate Kc, which is just 1 squared over 1.5 times 1.5, which is just, if you plug this in, 0.444. And this has bad sig figs, this question, so I'm not going to round or bother rounding. But let's see if I got that right, just to make sure, I guess. These are all other miscellaneous notes. Ooh, that's interesting. Contact process. So it seems like I lost the notes. Fear not, though, because we don't need these notes anyways. Let's do another example. The oxidation of NO to form NO2 occurs during the formation of smog. This is not that hard. Was found to be 6.78 at a specific... Okay, this one's a bit more interesting. So it gives us the balanced equation. So right away, let's put down what we know. Ice, and we have SO3, NO, NO2, and SO2. So, what do we know about I? Well, we know, for starters, this was found to be 6.78 at a specified temperature. So that's Kc. Kc equals 6.78. The initial concentration of NO and SO3 were this 0.03. And we know for sure this starts at 0 because it doesn't specify. What would be the equilibrium concentrations? So we don't know what they change in, so we'll call that x. In which case this is, sorry, add x. Because they're products, we add x. These ones will subtract x. Because it's 1 to 1 to 1 to 1, the changes are all to the x. They're all subtract or adding x. If this, for example, is 2, then we'd be subtracting 2x. But that's not 2, so we don't have to worry. We know that Kc is Kc, or 0.6.78, is equal to NO2 times SO2, our products. So x times x, which is just x squared, divided by SO3 times NO, which is just 0.03 x times itself, because we have 2 of them. How do we solve this? Well, in order to find the equilibrium concentration of each component, we simply take the square root, in which case we have 6.78 equals x over 0.0300 negative x. If we expand this, this becomes 0.0300 minus x, or it's actually 6.78 minus x 6.78 equals, this just equals x, and if you isolate, you get factor, you get x is equal to 1 plus 6.78, and that is just equal to 0.0300 6.78. So I'm going to just add a whole new page here. X in that case is equal to, let me just put this in my calculator, 6.78 divided by 1 plus roots 6.78. This is just 0.022. Right? We do that to 2 sig figs. Or actually we could do it to 3. I think we should do it. We should do it to 3 sig figs. That would be proper. Alright, let's do this next example. This one's actually valuable because, well, I'll go over why that is when it happens. But let's read this over. The thermal decomposition of water has a very small Kc. At 1000 degrees Celsius, Kc equals 7.3 times 10 to the negative 18 for the reaction H2O in equilibrium with 2H2 plus O2. A reaction is set up at this temperature with an initial H2O concentration of blah, 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 blah. So it gives us all this stuff. Let's set up our equilibrium ice table. We have ice. And we have H2O, G, in equilibrium with 2H2, G, plus O2. Now, let's see what it gives us. It says that initial concentration is 0.1 of H2O, 0.1. And we don't know what the initial concentration is of H2 and O2. We know it's 0 actually because it doesn't specify. Does it give us anything else? It gives us the Kc, so we're going to just go on and call this x. And let's call this 2x. Well, if we call this one x, we must call this one 2x because it's twice as much as this, right? Always look at your stoichiometric coefficients. And this is just going to be, again, minus x. And then we have 0.1 minus x And then we have 2x into x, in which case Kc, or 7.3 times 10 to the negative 18 is equal to this times this times this, or 2x squared, or actually, let's do that, another 2x squared x all over 0 minus x. Now, here's a problem. If we took the square, right, we still wouldn't get rid of this, because this is a cubic, right? Let me simplify this. This is really just 2x, or 4x cubed, my bad. Even if we squared it, it wouldn't really work out. We wouldn't get rid of it fully. So, what can we do here? What can we do here? Well, we can say, because the Kc is very small, the H2O concentration remains relatively constant. So x, or the amount it changes, is also very small. So for that, we can say that 7.3 times 10 to the negative 18 is equal to 4x cubed over the initial 0.1. You have to state that this assumption was made. Because, again, I'll go over that one more time. Kc was very small. So remember what we said about small Kc, it doesn't really proceed much to the right, it stays much to the left. Because it's very small, the equilibrium concentration of H2O doesn't really change, so we can simply make the assumption that 0.10 is the equilibrium concentration. If we go on and find what x is, x with a bit of algebra is just 7.3 times 10 to the negative 18, 5 by 4, and then 5. Raise that all to the cube roots. Should get 1.2 times 10 to the negative 6. So H2 would be 2 times this. So 2x equals H2, which equals times 2. 2.4 times 10 to the negative 6. That one was a bit more of an interesting question. I hope that helped a little bit. Let's do Gibbs free energy for the last one. Okay, let's see what it says here. So when delta G is negative, maybe we should first talk about what G is. G is Gibbs free energy, and Gibbs free energy is a measure of the amount of usable energy in a system, in a closed system, which can be harnessed or used. So when delta G is negative, a reaction is spontaneous, which means it will readily occur with a little bit of energy, and it occurs in the forward direction. It occurs to favor the product side. When delta G is positive, a reaction is non-spontaneous, and as a result, our reaction proceeds to the left. And when it equals 0, where our change in Gibbs is equal to 0, we are at equilibrium. But it's still technically spontaneous. Something else to note is that the position of equilibrium corresponds to the maximum value of entropy and the minimum value of Gibbs free energy. So what that means is, if we were to graph, for example, an equation, or just a general spontaneous reaction where delta G is negative, let's call this Gibbs free energy. And this is the reactant side. This is the product side. The change in Gibbs free energy, first of all, between the reactants and the product would be this right here, such that delta G is less than 0 or is negative. Another thing to notice is that equilibrium occurs right here, where delta G, the change in G, or the gradient of G, is 0. It's a minimum point. But this point, even though it's minimum in delta G, is a maximum in entropy. Entropy is essentially a measure of the number of different ways you can distribute energy amongst particles in a closed system. And when delta G is minimum, you can think of it as if delta G is at a minimum, entropy is at a maximum, because there's no usable, very minimum usable energy in a closed system, which means all that energy must be very finely distributed, and it must be at a maximum entropy. This corresponds with the equilibrium. And that's kind of what's going on there. You can also relate delta G to your gas constant, which is 8.31 joules per Kelvin per mole. And you can relate it to your equilibrium constant, Kc, for any reaction. Now, also notice that delta G will be in joules per mole if we're using 8.31 JK1 negative mole, or J to the K to the mole, or J over K over mole. Well, I butchered that. And ln T is in Kelvin, right? Temperature always in Kelvin. These cancel out, and that means our delta G is always joules per mole. If we want to convert that to kilojoules per mole, then we're going to have to divide by 1,000. In which case, that's really much it. Let's do this last question here. Calculate the value of the equilibrium constant of this reaction at 298 Kelvin. So let's do that. We know that delta G is equal to negative RT ln Kc, or just ln K, whatever you want to call it. We know that delta G is equal to negative 4.38 kilojoules per mole. Now this is a problem because, again, we said delta G should always be in joules per mole. So to do this, to kind of convert it, to fix our problem, we just multiply by 1,000. And we also want to find the K value. So we're going to isolate for this. We know that ln is just base. Well, first of all, let's isolate ln K. So we get delta G is equal to to delta G over negative RT. That's equal to ln K. We know that ln is just the log base E. So if we use our log laws, this just becomes E to the delta G over negative RT is equal to K, and then it just becomes a game of plugging it in. So K is equal to E, delta G in this case is negative 4.380 over negative 8.31, our gas constant, times temperature in Kelvin, 298. And let's plug that into our calculator. We should get, let's see what we get. We get that K is equal to 5.86. Unitless because K is a unitless value. Alright, thank you guys for watching. If you have any questions, feel free to comment down below, and I'll try and get back to you as soon as I can. Peace out.